My name is Fayed Hendley Elgart. I'm a PhD candidate at MIT.nano. I study the ice shelves of Antarctica, specifically the grounding zone, which is pictured here, which is the place where grounded ice sheets become floating ice shelves and ice, bedrock, and ocean all meet. This is a critical transition region in Antarctica. It's tens of kilometers wide, and it's a dynamic intersection of different parts of the cryosphere. Ocean currents converge and change directions there. Water gets sucked underneath the ice in the grounding zone as ocean tides lift the ice shelf off the bedrock. The bedrock can become saturated with water and change shape as the ice flows over it, and it's even host to abundant marine life. We want to figure out how fast warming ocean currents are melting the ice from below in the grounding zone. This can cause a feedback mechanism called the marine ice sheet instability, where when ice starts thinning and starts retreating because of ocean melting, it will keep retreating because ice is buoyant and wants to float. And to the best of our knowledge, that's what's happening now. Our research is trying to estimate how fast ice shelves are melting by making a better estimate of how thick the ice in the grounding zone is and how fast the ice thickness is changing. And we do this by combining remote sensing and simple physical models of the ice. We use laser altimetry, where a bright green laser from IceSat-2 orbiting the Earth bounces off the surface of the ice and returns to the satellite, where you can calculate how long it took for the photon to return and then what the height is of the surface ice. And then if you take two of those tracks, 91 days apart, because that's when the satellite ends up in the same place again, and you subtract those two repeat tracks from one another, what you get is the difference between what the surface of the Earth looked like at one point in time and another point in time. For the ice shelf in the grounding zone, that looks like this, where this portion is the grounded ice, which doesn't change much in between tracks. This portion is the floating ice, which is floating straight up and down on top of the ocean. It goes up and down with the ocean tides. And this portion in the middle, which isn't sitting still and it isn't floating, it's actually flexing. And that's the portion we can model as an elastic beam, sort of like a diving board or a bridge or a tectonic plate. They all obey similar equations. And we use those observations along with a model to determine the thickness of the ice. We want to be able to constrain the rate and amount of future sea level rise to ultimately quantify and reduce societal impacts of climate change. Sea level rise is accelerating, and it's projected to rise about 12 inches along the US coastline over the next 30 years, which is equal to the amount of sea level rise that's been measured over the past 100 years. Reducing uncertainty around sea level rise has real-world impact. The planning and preparation for a foot of sea level rise is very different for a meter or several meters, which is approximately the uncertainty in projections for the year 2100. We're trying to reduce those uncertainties.